welcome back. And welcome back to the Extremely Open Science EOS stream. We are currently live, and so we will start where we left off last week. But first let's do a quick recap of where we were. So this is our project called Sardine, so spelled with a Y. And last week what we did, let's just double check. Yes. So last week what we did is we developed this simulation. I still have it here. So sorry, let me just fix this quick. I am going to do something I probably normally would not do it this way, but now today I am going to do it this way. All right, I have some other processes running this, and I would normally go and find out what it is. Find out what it is, and I probably. Interesting. Yeah, sorry about this, guys. I'm just trying to find out where I have this other file open without sharing my whole screen. Weird. Actually, this one. Okay. Okay, where is it? Okay, that works. Okay, this works. Alright, sorry, yeah. So this is, I should reboot my computer every few weeks, I guess. So this is where we were last week. Yeah, so we developed this drug file. Let's read it from the bottom. So we got this E. coli genome. This is reference E. coli K12. We read the sequence, and then we choose a number of mutations, and this on the stream we had slightly different numbers. I updated this afterwards. So let's go from 0 to 50,000 by increments of 50. We create this mutated file using this very simple approach, and then we compute the size of the genes using Prodigal. Right, and it's probably a good habit to get into. So plans for today was to run checkm2 and then actually also trying a completely noised genome. So let's just see, if we have 8 ECGs, what's the, what would it look like if we ran Prodigal or checkm2 on that, right? So and then we ran this. So we ran this off stream because it was very slow, but it produced these plots, which I can show you. So if you look at the average gene length, it looks like this. Right, so the average gene length is 942 for the actual genome, and then it drops as the number of mutations increases. And so here, this is just a zoom in from on the same up to the initial, so it starts dropping quite quickly, so even a few hundred mutations you already have a drop. And if we look at the number of genes, the number of genes just increases. So, alright, so what are we doing today? So let's start, I'm gonna open it. So let's start with how we also saw how to run checkm2. So let's do that. Alright, so we saw this. Okay. So we had, so this is going to run, so this takes a while. So this is why I wanted to, let's do this first, and hopefully we will have set up the infrastructure by the end of the stream. Right, and we can see, I'm just going to run top just to see, yeah, okay, yes, as usual, OBS is running, so that's taking, the streaming itself is taking a lot, and but now we see diamonds also running, probably, and this is checkm2. So checkm2 is going to take a while, but let's also do the other plans. So actually, before we get to that, there's another thing, which is, so I'm gonna make this screen here a bit bigger. So we did this very simplistic mutation. Let's add some. And this was, it's took a string, returned a string. Right? Now this worked okay, well enough. The problem is that, you know, for a real genome, so for a real genome, so this like this, where so this should be about 4.6 megabase pairs. So, you know, 10 mutations, it takes this. Yeah, so it's not so bad, but you know, if we're going to be increasing this, it starts to get pretty bad. So, you know. So if we're going to be doing this over and over again, we can do actually much better. Let me just check on checkm2, it's still running. So I am also going to, okay, so let's have this as 2 seconds. We can do much better doing it in the following way. So instead we So the problem is that if we're doing with a sequence, if we're doing with a string, then every time we are going to be creating these strings, and we're going to be creating a new string. So if we do this instead with a list, then in fact we can just change those elements of the list. So the problem is that for a substitution, that's very trivial. For a deletion, that's not so bad either. This is a deletion. Let's actually do it like this. For an insertion, we can also do this, which is going to change that string. That string. So this is almost exactly what we had before, but it's not going to give you the exact same results, because once you insert a character in so let's say you have a sequence with 1,000 characters, and it starts as a string. Then you convert it to a list of characters. At that point, if you go to position 500, that's still the 500th character. But once you start mutating, so if you have a deletion or an insertion, now the position 500 might no longer be the 500th character, because there might be, so here when you delete, you might have removed a position. So this could potentially, and actually maybe here we should actually check. We should actually check that this is let's make it. Yeah, we should actually check that we are not deleting an empty. So if we do this, then it's effectively the same thing, not exactly identical, but effectively identical. And then now let's see, it went from, before it was 2 seconds, now it should be, yeah, so much, also basically scaling much better. So now we pay a significant cost at the beginning to convert from a string to a list of strings, and then a cost at the end to join all of them, but then the mutations themselves are almost instantaneous. So this is much faster, right? And so let's actually just let's just get this here. Okay, so I'm just going to commit that. So let me just check this again. Yes. And yep, that's it. Much faster. Oh. Okay. The results are, as I said, the results are not identical because the positions change a little bit, a tiny bit, but but they should be equivalent. I mean, these models are so simplistic that it really doesn't matter. Okay, and so here I am. Let me move this note. Okay, and now since we're here, now this simulation file also changed. So I'm going to I'm going to clean up, remove. So here, so Jug does not automatically detect that the results will have changed. So we have to tell it that any results from create mutated file are now invalid. So this was the invalidate command, and it invalidated all of the mutated files that we created before, but it also invalidated the gene sizes because they depended on the mutated files. So let's just rerun this. Particularly, let's just rerun it like this. Okay, this will run it in the background, and in the meanwhile, let's focus on checkm2. So we're going a little bit back and forth between these two, but checkm2 is the goal today. Okay, so here. So in principle, we should be able to run checkm2 on all or on at least multiple outputs at the same time, instead of one by one. Let's see if I don't work. Okay, so in principle this should work. Oh, might be a bit. Okay, let me check. I'm gonna do something a little bit different. Let's do it like this. Okay, yeah, let's do this. Checkm2. So I'm gonna be so I created this directory with links. no such file or directory. That's correct. Okay. Oh yeah, I love this feature of bloody Linux. So I created this directory. I created this directory. Let's see. I created this directory with links, and now I am going to feed it to checkm2, and see. And ideally, it should call all the genes in all of those bins. The reason I'm doing it that way is that so in the meanwhile, through running this multiple times, we had ended up with, so if we look at, I'm just gonna run this in the background. So if we look at the outputs simulations, there were a lot partial runs from previously, and they had accumulated. So I didn't want to have all of them at the same time. I wanted to be able to select. So one way you could do this is to create a separate directory that has only the things that we want to select, but without copying everything over, wanted to run just the ones we want. So we can create a directory, populate it with a bunch of links, call checkm2 on all of the links, and then that's it. Hopefully that should be it. All right. So how would we do that? All right. By the way, let's just check how the simulations are going. But I'm just gonna I'm gonna run a couple of so let's just create a here mutated files, okay, and then run. Let's do it this way. So we create and then run checkm2. So we need subprocess, yes, and we're going to. So we're going to create so I actually like to create a temporary directory, more because, and then I like to create a temporary directory and then use natural names inside that temporary directory. So for example, so checkm2 input directory, we can have it as something like this, checkm2. So and then copy would also work. But why? Probably want to create a sim link. This type of, I think we've literally, this is not the first time we've looked at this on the stream, how to create a sim link. It's not. let's do this one. So f is this sample. Okay, does this work? Yes. What we want is actually the opposite. So here, path. I'll do something. Yeah, something more like this. All right, check them. Yeah, let's see this, and this should. Yeah, okay, this works. Okay, I mean, okay, this works. Okay, and this also worked. Okay, I'm gonna take this. Okay, yeah. Yeah, okay. So I like to break, I'm gonna break this up a little bit into this is the plan. Okay, so this would work. The problem is, right now we're in the wrong environment, right? Conda. So to run this in Conda, we would want to have it in. We would want to. So we want to run this, but this. So we are running this in the Sardine environment, but the checkm2 is only available in the checkm2 environment. So this is not going to run. So what we need to do is so it's run is use conda run and then the command, and this is going to work. So, or maybe not. This will run now. Okay. So now we can't run it because I just accelerate this a little bit by let's accelerate it by first asking all the JAG processes to stop, and then once they have stopped, we are going to run just the creation of the simulation. So let's just run just the creation of the outputs, and this will be significantly faster. So as I said, this probably is going to take and let's see how we're doing. Yep, okay, so now this is going to take a little bit of time, but in the meanwhile, let's go to this is still running. Yeah, this is still running. It's still so the other one, the one that we run for test with only 30, it's still running. So maybe not so great, but so we still don't have the quality report. Let's actually see. Yep, they're still running this big diamond process. Okay. Okay, I guess it has done some pre-processing for the initial genomes, but not everything has finished. Okay, so this also probably means that we might not be able to do.
Good morning, TRI. Today we have our special One TRI Reconciliation Week event, where our TRI partners will showcase projects advancing Indigenous health outcomes in the auditorium from 10 a.m. This will be followed by bush tucker treats in the atrium. Well, everyone is welcome. We really hope to see you there.
Alright, so we have some local events being announced. Yeah, unfortunately I don't think that people on the stream can attend, but yeah, I don't know. Alright, so where were we? Alright, let's see. So we've managed so far to run CheckM2. It's running. It's going to take a while, but hopefully, so right now then the hope is that we will be able to set it up, press the run button, the JAG execute command, and then it will run, and it will take probably a while, and then I will post the results on the mailing list. So in the meanwhile, this is also running. So you can see it took, it was a couple of minutes, and it went from 125 complete simulations to 175. So that was 50 in pretty short amount of time. So this will run. This recreation of the simulated files, this will finish, but the rest will not. Okay, so the other thing we actually had for today was to create a completely random file. So just run that with a completely random file. So let's start, and just for the sake of it, let's do it in a not so trivial manner, or still fairly trivial, but not completely trivial. So there's a question in the chat. What's the difference between how we were running CheckM2 in the previous stream? So now we are running it, giving it a directory as input, and it will just process all the files in that directory. And because it relies on Diamond, I think this is faster than doing them one by one, because Diamond is much faster if you give it many sequences. So the trick with Diamond is that it scales very well. So if you give it one sequence, it's actually pretty slow, but if you give it 10 sequences, it's not 10 times slower. And if you give it 1,000,000 sequences, it's not 1,000,000 times slower. So by giving it as many inputs together as possible, I think we end up using the computation the most efficiently. And also now we also before we were just running it on the command line to test, and now we wrote Python code that will create an input directory, put everything nice for it, with all the symlinks, but only those symlinks, and then call it. So let's create a mutated file, let's create a complete. So we have E. coli. Okay, so we have here. So this would work. Something like this would work. Yeah, this would actually work pretty well. Let's just do this. So there's so we could do a little Markov chain. I'm actually just checking. Okay, so one idea, and this is very standard sort of bioinformatics from the olden days, is to do a little Markov chain. So that what this would mean is, so instead of doing ATCG, we can start with, we have to figure out how to start, but let's say if you start, let's say AT, then the next nucleotide is not random ATCG, or not uniformly random, but you look in the original or your training sequence and you see what's the distribution that follows A and T. So if after AT, maybe A is much more likely than maybe A is much more likely than T, and C and G are equally unlikely. So something like that. So what we need to do is, so first actually we start by counting from how often we have the, so if we're doing a chain of size 2, so we look at 2 letters to determine the third, then we need to count how often each triplet appears. Okay, I think this is correct. Work. Let's count keys. That's correct. I think okay, the first step, this is a little bit silly. So sorry, I might need to. So this part is correct. So okay, this is not very good. Let's see. Yeah, this is pretty good. Okay, yeah. So okay, so we need to find yeah, okay, this is fine. Oh yeah. It's not very clean code, to be honest, but very clean code, to be honest. But so let's do this. So here, new seek is, so it's a list of characters, right? And yeah, okay. Alright, so this would work. Alright, so this works. So this is, alright, let's just, okay, I'm not a big fan of this. Okay, so Markov, so alright, so we created, generated DNA random sequence with same length as using a Monte Carlo chain of size MC len. Right, so product, we don't need product. Traces. And so every time, so we start by counting the number of times that, so let's say we have k equals 2, so the number of dinucleotides, so the number of times, and then the number of trinucleotides. And so this is obviously a little bit redundant because, but little bit redundant. So actually this one, so then what we do is we, for each one, let's just keep ATCG. So and then we create this probability, which depends. So let's just check. See, so for example, we can see that if we have a C and a C, it's very likely to have, much more likely to have an A than if we have a G and a T, right? So if we have a CC, A is 30% probability, and after G and the T, it's only 20% probability. So you can see actually this is the sort of the range, but you know, it's between 20 and 30. So yeah, okay. So an A rarely follows C and T. So this is fairly simplistic, but it does work. So now let's create the generate. So what did we create? Yeah, let's use create. Let's test a couple. Okay, so let's just do this. So, and so yeah, this would work. First of all, let's just see. Okay, let's just see. Okay, at least, at the very least. Okay, we should be able to create random files. Okay, it's taking a little bit longer than I expected. No. But there it is. Counts, so yes, of course, mclen and mclen plus 1. Alright, so, okay, we are slowly running out of time, so I'm going to do okay. So we're slowly going out of time. So I'm gonna stop everything. Okay, and then so this should finish. They're finishing one by one. It doesn't. Now what I'm going to do is I'm going to here. Let's do this. So if I do this, so if I just want to run from yeah, okay. So if I just want to run from 0 to from 0 to 5,000, everything is so that's mostly done. So I'm just going to make sure that we run everything. So you can see now, so if we're running, so it's still creating one of the mutated files, but it's finished, it's finished creating all of the mutated files, still creating one of the random ones. So the gene sizes, this is still waiting, but the run check M2, we can also run it already. So I just want to, at the very least, check that it runs, that it at the very least doesn't immediately crash. So here, this one is still running. I'm gonna kill it because it's, so this is a bit too much to run on the stream, but it will finish in a few, it will finish eventually. So what I'm gonna do is I'm just, so let's just see. Okay, see? Check run, it's not check run. Check call. Put a little bit of yeah, so this is running something. Yep, so it's running the background somewhere. There it is. On the run, and yeah, okay, so this everything runs, so everything runs, the simulation runs, everything is fine. So it's still creating one of these random files actually. So let's just look a little. Yeah, this is how. Okay, that's the. Okay, maybe not surprising that it's the uniform of size 4 that's taking a little bit longer. Well, I mean, I'm not sure why it would be. Well, anyway. I don't know, this shouldn't be that. Okay, so the average gene size, if we just use a very simplistic model, is 166. 180. So this is nucleotides, right? So this is we're using nucleotides here. So if we compare with the what we had, average gene size. So this is simulation. So so even with a lot of mutations, we still have some signal there. So that's not. Okay, so let's close up. So which means so we did a lot of work. Normally I would have broken this up a bit more. So which maybe I am actually. The way I'm going to do this is I am. Okay, let's. Let's create. All right, let's just commit this. Yes. No, that change we do not want. This change we want. Okay, so this is create random genomes. To a project. And then let's put back. Okay, so here what I did, and this is a little bit of so I temporarily just deleted the things I did not want to commit and putting everything back now. And now I can check into no actually that one yeah. Okay. Okay, so I messed up a bit here. Okay, here, let me just, yeah, so, right, so this is what we had at the end now, except I played around a little bit with the, I played around a little bit with the number of mutations we wanted but now, so I'm just going to write some notes, and then I'm going to leave this running. It'll probably take a couple of hours maybe even until tomorrow. And when I will record a recap video, and then in the recap video I will show the results of running this. So I'm running everything on my laptop. So this is also, we could potentially just farm it out to a cluster, and this would be done in a couple of minutes. But I do want to, so this project, I do want it to be something that, anybody can run. It might take a couple of hours, but this is a nice laptop. If you have a slightly older machine, maybe it's going to take, maybe you need to run it a little bit overnight, but there's nothing here. There's nothing here that, so we created half of these files on the stream, and when I'm not streaming and I don't have OBS running, this is much faster as well. So stream notes. Well, at least we create. Okay, and then for next week, which will be the oh, this doesn't exist anymore. So let's just check. So this will be the 4th. So we will look, compare. So we'll compare checkm2, simulated data, checkm2 with our data. Let's see what we should do. So then I think at that point we will have a good idea whether this makes sense. Maybe we will broaden this a little bit now that we have this infrastructure and explore a different genome. Not a completely random sequence, different genome, and apply a different genome, high quality isolate. And then maybe we should also check gene sizes on lower quality isolates from progenomes. And then, so I think this would be good plans for next week. Okay, so there we are. Bitstream notes. Okay, so as I said, all right, I will now. Oops, sorry. I will now run this. I'll just leave this running. Everything will run. Everything will run. And then once this has finished, I will post the results also on the mailing list. I will share everything. I'll put them on the recap video as well, the results of this, and then I'll see you next week, where we'll continue doing that. So meanwhile, if you're watching, if you're not subscribed, please do subscribe. Join the mailing list. Tell us what you think, and yeah, and I'll see you next week.